Greetings. Welcome to today's session. So today we will continue from where we left off. So if you recall, till the last lecture, we were pretty much sort of like recapping what we had already studied as far as the notions of linear time invariant causal systems and representation of system models using transfer function and poles, zeros, and then impact on the system response. Also, like the notions of bounded input, bounded output stability, and performance specification. Right. So these are concepts that we looked on till the previous class. So today we will look at the closed loop system per se. Right. So, but before we go into that, just and we draw equivalent diagrams. Just one point which I want to highlight is that, like, let's say we have a plant, whose transfer function is some P of S, and the input to the plant is the Laplace transform. The input is U of S, and the Laplace transform, the output is Y of S. So we can immediately note that P of S is defined as Y of S by U of S, and alternatively, Y of S can be written as P of S times U of S. Right? So that's something which we are aware of. So the one way to interpret this graphically is that if we have sort of a block diagram representation, like of this idea, we can immediately observe that if I write the transfer function of a block, the output signal from the block is going to be the transfer function multiplied by the Laplace transform of the input signal. Okay, so that's something which we can immediately observe. Right? Is it not? So I am going to use this notion to explain the overall block diagram of the closed loop system, and essentially then use that to what to say, derive some standard functions, okay, in this particular class. So please observe how I am drawing the block diagram now. So let us say we start with the plant whose transfer function is P of S. So the input is U of S and the output is Y of S, right? So our objective in the so-called output feedback problem is to regulate the output around some R of S. So let us say we have the feedback path, and in the feedback path, let us say we have a mapping H of S. For example, we may have a filter to filter out noisy signals, right? Or we may be measuring a quantity which is different from what we want to control. For example, if we are measuring, let's say, acceleration and we want to regulate speed, okay, like we may need to integrate the acceleration signal, right? So then we may want to put an integrator in the feedback path and so on, right? So in those scenarios, like we may have a feedback path transfer function. So we take this. So let's call the signal which is coming out of this feedback block as some W of S, okay? And this goes to the summing junction, and we get an error which we denote by E of S, and this error now goes to the controller block whose transfer function is C of S, okay? So what is, let me introduce all these terms very carefully. So P of S is the plant for the system transfer function. Okay, C of S is the controller transfer function. Okay, and H of S is what is called as a feedback path transfer function. Okay, why is it called feedback path transfer function? Because H of S is the transfer function is the feedback path, correct? So that's why it is denoted or named accordingly. Right? So these are the what to say, various quantities. So please now observe how I'm writing the equation. As I discussed just a few minutes back, if we have this block diagram representation and we are given the transfer function of a block, the output signal from the block, okay, in the complex domain is going to be the transfer function multiplied by the input signal to the block. Okay, so that's how we are going to write these functions. Okay, so consequently, y of s, which is the output from the plant transfer function block, that is going to be P of s times U of s. Once again, I'm reiterating that plant transfer function is P of s, the output is Y of s. So the output is going to be the block transfer function multiplied by the input. Okay, it is U. Okay, so that's how we are writing. All right. So now similarly, what do you think will be U of s? U of s is the output from the controller transfer function block. Right? So the controller transfer function block output is P of s. P of s multiplied by E of s is going to be U of s. Right? So this is U of s. Okay, so I hope it is clear how we work. Right? So just we write that I'm just interchanging C and P. Okay, we write the C of s times P of s and E of s. E of s now is going to be R of s minus W of s. Right? So because how this is E of s. Right? So moving ahead, so this we are going to get there. So now we are going to call the C of s times P of s is denoted by D of s. Okay, so what is D of s?
Professor,
Yes, please.
that R of s minus W of s, is it a modulus of R of s minus W of s, or sign also we need to consider?
Sign we need to consider. It's square bracket. Okay, let me put a parenthesis. Okay. Okay, so 1 minute. Let me. We need to consider the sign. Okay, so let me put a bigger parenthesis just to clarify that. All right.
Okay.
Okay. So what is this G of s? This quantity G of s that we are defining is defined as the product of the controller transfer function, the plant transfer function. Suppose, let us say we draw a block like this. Okay, just a fictitious block. Okay, in what is called as the forward path, as we have already learned. Okay, so this is the forward path. In the forward path, we have two transfer functions, right? So G of s, C of s, and P of s. So this G of s, which is defined as the product of C of s and P of s, is what is called as the forward path transfer function. All right, so that is what it is. Okay, so this is called as the forward path transfer function. Okay, so let me come down here. All right, so going ahead, so we have Y of s to be equal to G of s times R of s minus G of s times W of s. So what is W of s? W of s is going to be equal to H of s times Y of s. Right? So this is W of s, because W of s is the output from this block, right? So whose transfer function is H of s and the input to the block is Y of s. So you can see that I am just doing very simple algebra. Okay, so essentially to convey this. Of course, if you recall what was this block diagram, you know, like this is a block diagram representation of a closed loop negative feedback control system, right? So this is something which we have already looked at. I'm just reiterating this. Okay, so this is the block diagram of a closed loop negative feedback control system, right? So that's what we are analyzing. So this will be W of s. Okay, so now we can immediately observe that we have Y of s on the left hand side and the right hand side. So what will happen here? I can combine the terms involving y of s. So this will give me 1 plus g of s times h of s. This is going to be equal to g of s multiplied by r of s. Okay. So consequently, y of s by r of s is g of s divided by 1 plus g of s. Okay, so this is what is called as the closed loop transfer function. So we are going to shortly see why it is called. Okay, so let me first write down what it is called. And it is called as the closed loop transfer function. Okay, abbreviated as CLTF. Okay, so we are going to call it as CLTF as an abbreviation. It stands for the closed loop transfer. So why is it called closed loop transfer function? Let us say I draw a big block, okay, around all these smaller blocks, okay, and let us say the input to the big block is R, right, R of n, and the output from this big block is Y of n, output, right, the system output. So let us say we draw this big block, which encompasses all these smaller blocks. You can immediately observe that this big block, if I draw like this, is going to have an input of R of s and is going to have an output of Y of s, right? And the corresponding transfer function is going to be equal to G of s divided by 1 plus G of s. Okay, so I hope it's clear why it is called the closed loop transfer function. So consequently, if you draw a complete block, right, around this closed loop system, this what to say is what is called as the closed loop transfer function. All right. Okay. So I hope it is clear, right? Why it's called as a closed loop transfer function. All right. So now let's please once again please stop me if you have any questions at any point in time. We are just deriving some important concepts and terms. All right. Okay. So now, if you look at the closed loop transfer function, it is a ratio of two polynomials in S, right? Is it not? So the zeros and the poles are what are called as the closed loop zeros and the closed loop poles respectively. So point number one, okay, what do we know? That is the following: the zeros and the poles of the closed loop transfer function are called as closed loop zeros and the closed loop pole respectively. Okay, so that is point number one. Now, the second point is the following. If you look at the denominator of the closed loop transfer function, we have the polynomial 1 plus d of s h of s, right? So the polynomial 1 plus d of s h of s is what is called as the closed loop characteristic polynomial. So what is so special about this closed loop characteristic polynomial? Closed loop characteristic polynomial's roots are the closed loop. Okay, so that's what is special about the closed loop characteristic polynomial. So we can immediately observe that the closed loop characteristic polynomial is 1 plus d of s, and its roots are the closed loop. Okay, so and then the equation 1 plus g of s h of s equal to 0 is what is called as the closed loop characteristic equation. So once again, what is special about this closed loop characteristic equation? Its solutions are the closed loop codes, right? So we solve 1 plus g of s h of s equal to 0. We get the closed loop poles once again. All right? Yeah. Okay. Fine. So these are the some important terminology, right? So that we will encounter. All right. So now I'm going to draw the same feedback diagram, okay, in a certain way. Okay. So what I'm going to draw, so let me redraw what I drew first, and then we will discuss. Okay. So initially we had drawn the feedback diagram, the closed loop feedback diagram in this way. So we had the plant transfer function to be C of S. Then the reference input was R of S. And uh, the feedback path transfer function is some H of S. Then we bring it back here and we compare, and then we get E of S, and then we have our controller transfer function C of S. Okay, so this one, what I'm going to draw is that I'm going to redraw like this. Okay, so typically you will see that many feedback loops are drawn like this. Okay, so what people will do is that they will many times combine this controller and plant block and call this as G of S, right? Because as we know, the forward path transfer function G of S is defined as the product of C of S and P of S, right? So now the input to G of S will be E of S. The output from G of S block will be Y of S. And then what will happen? There will be R of S, okay, which will be compared with W of S. Okay, and this is what we have. All right. So this is an equivalent diagram. So we can see that these are two equivalent diagrams, right? So only difference is that we have just returned this P of S, we have replaced the P of S, P of S blocks that appeared separately before with one single block, right? So which will be the G of S block. All right. So that's what happens in this case. Now, if we look at this block and we evaluate what is W of S, okay, so we can immediately see that W of S is H of S times Y of S, and Y of S is going to be equal to G of S times Y of S. So this implies that W of S is equal to G of S H of S multiplied by G of S. Okay. So why are we looking at this? This has a special connotation. So just imagine that we are breaking open the loop here. Okay, suppose just picturize that we break open the loop at this junction, at this summing junction. Okay, so what we are going to get is the signal W of S. Just consider a fictitious system. Okay, so if we consider that, we can immediately see that the output of that fictitious system will be this, and the input to the system will be E of S. Okay, so consequently, this quantity G of S times H of S is given a special name. Okay, it is what is called as the open loop transfer function. Okay, abbreviated as OLTF. All right. So what is this open loop transfer function? If we were to be very precise, it is the ratio of W of S by G of S. Okay, which in this case is G of S times H. Okay, so this is what is called as the open loop transfer function. Okay. So why is it called open loop transfer function? As you can see, we are getting this definition, this transfer function by opening the loop, right, within quotes, right? Yeah. So we are fictitiously cutting open the loop and then getting this transfer function. Please note that this is a fictitious quantity that we are going to use for convenience in our analysis of the closed loop control system. There is a difference between this open loop transfer function, which is g of s times h of s, and the transfer function of an open loop control system. So please note that an open loop control system will not have feedback, right? And so it will have its own transfer function. Okay, so we are not talking about an open loop control system here. Okay, so the adjective open loop before the word transfer function or before the term transfer function does not indicate that we are dealing with an open loop control system. Okay, so please keep that in mind. Okay, so there is a subtle difference between the transfer function of an open loop control system, which is completely different, and the open loop transfer function that we are defined here. Right? So now the poles and zeros of G of s and H of s, okay, are called open loop poles and open loop zeros respectively. Okay, so that's the term. All right, so the poles of the open loop transfer function are called open loop poles. Okay, the poles of the the zeros of the open loop transfer function are called as the open loop zeros. Right, so those are some terms. All right. So now, if we look at how this is correlated to our analysis, immediately we can see that the closed loop characteristic equation, which is written as 1 plus g of s h of s equals 0, can be rewritten as 1 plus the open loop transfer function equals 0, right? So one can immediately see some connection coming up, right? So we will start utilizing this connection as we go along. Okay, so please note this connection. Okay, so that is like there is a link between this open loop transfer function and the closed loop characteristic polynomial or the closed loop characteristic equation. All right. So please note that. Okay. So I hope these definitions, these notions are clear. So let me recap what we have done. We have considered the closed loop control system with negative feedback. Right? And then we have essentially looked at the equivalent standard block diagram. We have used the fact that when we represent in the block diagram representation, the output signal in the Laplace domain, the complex domain, is going to be the block transfer function multiplied by the Laplace of the input signal, right? So that's something which we have exploited. We have used that to essentially derive the closed loop transfer function, okay? And we have identified what is called as the closed loop characteristic polynomial, closed loop characteristic equation, because those are important, because the roots of the closed loop characteristic polynomial are the closed loop poles. And once again, the solutions to the closed loop characteristic equation are the closed loop poles, right? So, and we have also looked at a term called as the open loop transfer function, which in this case is g of s times h of s. All right. So these are the key concepts that we have discussed till now.
Professor, if one plus open loop transfer function is equal to 0 means whether open loop transfer function is equal to -1, can we take in that way?
So, okay, that's good. What to say? Essentially, let me essentially comment on that. Okay, So if you look at 1 plus open loop transfer function equal to 0, this essentially means that if I rewrite the same equation as g of s h of s equal to -1, okay? So that's how it can be rewritten, right? Is it not? Right? If we write the g of s h of s equal to -1, what it means is that like those values of s, okay, the complex variable here, at which the value of the open loop transfer function becomes -1 or closed loop pool. Okay, that's the correct interpretation. Okay? So values of the open loop transfer function becomes -1 or closed loop. All right? Yeah. So g of s h of s equals -1 doesn't mean that the open loop transfer function is always -1. I hope that subtle difference is clear, right? Because 1 plus g of s h of s equals 0 is the closed loop characteristic polynomial, right? And 1 plus g of s h of s equals 0 is the closed loop characteristic equation. So if we rewrite g of s h of s equals -1 or the open loop transfer function equals -1, it does not mean that the open loop transfer function value is always -1. I hope that subtle point is clear.
Yes, clear, sir.
Yeah. So the correct interpretation is that this is a good question. You know, like the correct interpretation is that what we can interpret from this equation g of s h of s equals -1 is that those values of s at which the open loop transfer function's value becomes -1 are closed loop. Okay, so that's the correct interpretation. All right. Yeah. Okay. So now moving ahead, I'm going to leave this as an example problem exercise to you. You don't need to submit them as homework. So suppose if we consider this, everything remaining the same, but then we have positive feedback. Let us say suppose we have a similar block diagram, but the main change now is that like rather than negative feedback, we have positive feedback. Okay, so I leave it as an exercise to do. Okay, I'm sure you can do similar steps, but please do them as an exercise. I just want you to show that the closed loop transfer function with positive feedback is g of s divided by 1 minus g of s. Okay, so you can immediately observe that the only change is that in the denominator, instead of 1 plus g of s h of s, we will get 1 minus g of s. Okay, so consequently, the closed loop characteristic polynomial is 1 minus g of s h of s, and the closed loop characteristic equation is essentially 1 minus g of s h of s equal to 0. All right. Okay. So this, please do it as an exercise. I'm sure this can be easily done. All right. Okay. Now, if you look at this closed loop characteristic equation, please note that there are three quantities. Okay, in the overall problem. So, what are these three quantities? The first quantity is the plant transfer function. Okay, this is typically known. Right? Why? We synthesize using a system model. Correct? So suppose if we are looking at controlling the heading angle of a vehicle, right? We can use the bicycle model that we learned in vehicle dynamics to get the plant transfer function. So we essentially derive the equations of motion, and this plant model is synthesized. Okay, so that is one. Then the second thing in this equation is this feedback path transfer function, which is also typically known. Right? So, for example, we can have unity feedback, right? If we have unity feedback, this, what to say, this will be one, right? As far as unity feedback is concerned. But if we have non-unity feedback, like we are going to get something other than one, right? So, in this particular case, all right? So that's something which we know, all right? So H of S is typically known, right? And the only other quantity in this entire block diagram is the controller transfer function, which is what is under our choice, right? So the overall problem boils down to choosing C of S such that the closed loop system is stable and meets performance requirements. So I hope the problem becomes clear, right? So what we are going to do in this problem of controller design is that, like ultimately the problem boils down to figuring out what the C of S would be, like, so that, like we can then start working on, getting this uh, transfer function, right? Controller transfer function such that the closed loop system is uh, stable and also meets the performance requirements. Okay, so these are the three quantities that are part of this feedback loop. Okay, so once again to summarize, the plant transfer function is typically known, right? So we know them. We essentially can derive the equations of motion of the system or the plant under study, and we can apply the Laplace transform to obtain the plant transfer. Okay, so it's typically given, it is known, it's fixed, right? H of S is the feedback path transfer function. Once again, it is known, right? And C of S is the controller transfer function. That's what we want to say. And typically, what we will realize is the following, right? So by and large, we will realize that the structure of the controller transfer function is also like fixed. Okay, that is, we will choose what the transfer function structure should be, and the overall problem boils down to figuring out certain parameters, okay, in that structure. Okay, we will look at it in the following lecture as to what are some common controller structures we will be choosing, right, for designing control systems. And we will see that overall the problem boils down, to uh, figuring out these parameters, right, that appear in the controller functional form. Okay, so in essence, if I can take an example, if you want to do an example of designing a controller, for regulating the lateral position or the heading angle of an autonomous vehicle, we will know the plant transfer function. Like ultimately what it boils down to is that like we need to design the controller transfer function. And typically we will also choose the controller transfer function structure. Ultimately, the overall design problem reduces to uh, figuring out a few parameters, okay, associated with the controller transfer function. Okay, so we are going to look at various choices for these controller transfer function. But what I am going to give you as an exercise in this, in this context, is that please refer to our notes, okay, from the vehicle dynamics course. Okay, so please refer to the notes from the vehicle dynamics course, and you find out various models that you have derived. See, let it be the bicycle model, or let it be the quarter car model for suspension, right? Or let's say some other relevant models like roll model or pitch model. right? So you essentially identify those models and get the corresponding plant transfer function. Okay, so I will write down what this exercise is. So refer to the notes of our vehicle dynamics course. Please do this, because we will be using them, okay, as we go along. Referring to the notes of the vehicle dynamics course, what you do is that, like, identify a few plant transfer functions. Okay. And think about the control application for which they can be used. So, for example, the bicycle model can be used for lateral control, heading angle control, and so on, right? So, the quarter car model can be used for right control and so on, right? So just think about the control applications for which they can be used. Right? Please think about that. Okay. So now the overall problem, as we just discussed, like we essentially are going to look at this controller block. Okay. So if you look at the controller as a standalone block, okay, in the overall scheme of things, please recall that the controller will take in the error, right, from the summing junction and will give the plant input as the output. Okay, so the input to the controller block is the error signal, and the output from the controller block is the control input, right, which goes to the plant. And if we essentially look at it in the complex domain, P of s will be the controller transfer function. E of s will be the corresponding Laplace of the error signal. U of s will be the corresponding Laplace of the input control input. So consequently, our U of s will be equal to C of s times E of s. All right. So this is what we will be looking at next. That is, the question that we will be asking ourselves is the following. So what choices of C of S are commonly used, and then what happens with those choices, right? So essentially, if we are dealing with those choices of the controller transfer function, how will the controller design problems will boil down to? Okay, so that's something which we will look at in the next class. Okay, fine. So any questions about the material that we have discussed in this class?
No, sir.
Okay. Okay. So if not, I'll stop this session here, and we'll continue the next.